Mr. Antonucci here, and in this video we're going to talk about finding average velocity and instantaneous velocity, as well as finding the derivative of a function at a number. So average velocity is simply an application of average rate of change to an actual physical situation. Some key terminology: initial position. This refers to the object's location at time t equals 0. Sometimes other times than t equals 0 are used, but typically t equals 0 is going to be the initial position. The position function, this is going to be the function that models the position of the object as a function of time. And also rectilinear motion. This is how we refer to motion along a line. So if you think about driving in a car, your initial position would be where you're starting. The position function would model where you are with respect to time. On the screen is the definition of average velocity. What you want to understand is that average velocity is the change in position divided by the change in time. So it's how fast on average the object was moving over an interval of time. Let's look at an example for finding average velocity. Suppose I was standing on the bridge that crosses over the Colorado River at its highest point, which would be 890 feet above the river. I was taking a picture with my phone and accidentally dropped it off the bridge. This is a totally fictitious example, however. My wife timed how long it took for the phone to splash in the water, and it was approximately 7.458 seconds. We want to know what was the average velocity of the phone on its journey to the river. To do this, we would get the change in position over the change in time. So if it took 7.458 seconds, that's how long the change in time was. And you could think of that as 7.458 minus 0. And then the numerator, the change in position, is going from 890 feet to 0 feet. You would get 119.335. And the units would be feet per second. If you remember, the numerator was the change in position in feet. Denominator is change in time in seconds. So the units are just change in position units divided by change in time units. While the average velocity tells us how fast the phone was going on average over an interval of time, it doesn't tell us about the velocity at any particular moment in time. If we want to investigate the instantaneous velocity of the phone, for example, at 3 seconds, we would need to compute the average velocity over an interval starting at 3 seconds to some other time, like maybe 3.5 seconds, and then we would take the limit as t approaches 3. We can use the position function f of t equals 16t squared to model the distance the phone falls in feet as a function of time t. We can do this quickly and accurately in Desmos first, and then we'll come back and prove it analytically. Let me explain what I have here. So first, up here I have the position function 16t squared. Then I have the initial position at t equals 3, which is 140. And then in the table here, what I did was I set up the first column as the second time value, which is going to be some time after 3. And then in the second column, I put the formula for average velocity. So if I plug in 3.5 here, it's going to automatically calculate for me the average velocity between 3 and 3.5 seconds. Then I can just let the second time get closer to 3 without actually equaling 3. So 3.25, 3.1, 3.01, 3.001, 3.0001. And I can keep going here. It looks like as T2 approaches 3, the average velocity is approaching 96 feet per second. Let's go ahead and prove this analytically. What we were doing on the table was taking the limit as t approaches 3 of f of t minus f of 3 all over t minus 3. If we plug those values into the limit, we'd have 16t squared minus 144 over t minus 3. We could simplify this by factoring out at 16 and then factoring the difference of squares. You can see a factor of t minus 3 would cancel, and this would leave us with the limit as t approaches 3 of 16 times t plus 3. Then if we let t approach 3, you'd have 16 times 6, which is 96. And again, the units would be feet per second. And this confirms our conjecture that we had from the table that the instantaneous velocity of the phone at 3 seconds is 96 feet per second. So here's our actual definition of instantaneous velocity. It's basically just the limit as the change in time approaches 0 of the average velocity. Let's go ahead and do an example. We're going to find the velocity of the falling phone from the previous example at t equals 1, t equals 7.4 just before it hit the river, and at any time t. So for part A, we'll do the limit as t approaches 1 of f of t minus f of 1 all over t minus 1. And that's going to be 16t squared minus 16 all over t minus 1. Now, if we take the numerator, you can factor out a 16. And then the t squared minus 1 is going to be a difference of squares. So 16 times t minus 1 times t plus 1. And then the factors of t minus 1 in the numerator and denominator will cancel. This gives us the limit as t approaches 1 of 16 times t plus 1. Now, as t approaches 1, you would have 16 times 2, so this will be 32 feet per second. For part B, we do the same exact process. We take the limit as t approaches 7.4 of f of t minus f of 1 all over t minus 7.4. Then we'll show you a little trick here for being able to evaluate the next part of the limit where we plug in the values. So we're going to leave the 7.4 squared as is and not simplify it any further than that, because we can now factor out a 16 from the numerator, and then we would have t squared minus 7.4 squared, which we could factor as difference of squares. Then, of course, the t minus 7.4 would cancel, and this simplifies to 16 times t plus 7.4. If we take the limit as t approaches 7.4, we would have 16 times 14.8, which is going to be 236.8 feet per second. For the last part, we're going to do this in general. So at any time t, so v is the limit as t approaches t naught. And t naught just stands for the initial time. F of t minus f of t naught all over t minus t naught. We plug it into the functions. We would have, again, we could factor out a 16. Then we would have a difference of squares. We could further factor that, and we would have the t minus t naught factors cancel. And we'd be left with 16 times t plus t naught. If we take the limit as t approaches t naught, then we would have 16 times 2t naught, or 32t naught. In other words, whatever we pick for our initial time, we would multiply by 32, and that would give us the instantaneous velocity at that moment in time. Now we want to talk about how to find the derivative of a function at a number. That first limit we learned in this section, f prime of c, is essentially the same limit that was used to find the slope of the tangent line, the rate of change of a function, and the instantaneous velocity of an object. These are all grouped into the mathematical concept called the derivative. And here we have the definition of the derivative. The function's defined on the open interval a to b, and c is on that interval. Then the derivative of f at c, notated with the function f prime of c, is the number f prime of c, which is the limit of that quotient. Let's run through an example so we can see what we're talking about here. We want to find the derivative of f of x equals 2x squared minus 3x minus 2 at x equals 2. In other words, we want to find f prime of 2. Using correct notation, we're going to write f prime of 2 equals the limit as x approaches 2 of f of x minus f of 2 all over x minus 2. Plugging in f of x is 2x squared minus 3x minus 2 minus, now off to the side we can do f of 2, and that's where you plug 2 into the function. So 2 times 2 squared minus 3 times 2 minus 2, which is going to give us 0 all over x minus 2. Just a word of caution, you're not always going to get 0 here, so just be careful. Then we can factor the numerator all over x minus 2. And you guessed it, the x minus 2's cancel. So we have the limit as x approaches 2 of 2x plus 1. And as x approaches 2, the limit's going to be 5. So we would say that f prime of 2 equals 5. Now I'm going to show you how to do this in Desmos. This can be very helpful in checking your solutions for this section, but you also want to know how to do this analytically and make sure you have the background algebraic skills to be able to do this. So in Desmos, we just enter the function, and then in the next line, you literally type in f prime of 2, and it gives you the answer 5. Again, this is a way to check the answers that you're getting analytically. You can't always rely on just going into Desmos and getting the answer that way. To this point, we've had three interpretations of the derivative. The geometric interpretation, so if y is a function, the derivative f prime of c is the slope of the tangent line to the graph of f at that point. The next interpretation was the rate of change of a function, and f prime of c in that context represented the rate of change of the function at c. And then finally, the physical interpretation, where f prime of c or f prime of t naught would represent the instantaneous velocity or just velocity of the object at time t naught. Another classic problem that we're going to run into again and again and again and again is finding the equation of the tangent line. We're going to do this in 3 steps here. We're going to find the derivative of square root 2x at x equals 8. We're going to write the equation of the tangent line at that point, and then we're going to put everything on a graph in Desmos. For part A, when it says find the derivative of f at x equals 8, the notation would be f prime of 8. It's important to write that and then use the limit definition there. Limit as x approaches 8 of root 2x minus f of 8. If you plug 8 in, you would have square root of 2 times 8 or 16, which is 4, all over x minus 8. Now you can't cancel anything here, but we can simplify this by multiplying by the conjugate. So root 2x plus 4 over itself. So the denominator doesn't get distributed, you just leave it as 2 factors. And the conjugates, you FOIL those out. When you multiply the firsts, you'd have root 2x times root 2x, which is root 2x quantity squared, which is just going to simplify to 2x. When you multiply the outers and the inners, they'll be opposites, so they cancel. And then the last would be minus 16. And you probably guessed it, the numerator we can factor out a 2. And the factors of x minus 8 will cancel, leaving just the 2 in the numerator and the root 2x plus 4 in the denominator. Now, if we take the limit as x approaches 8, the denominator is going to go to root 16 or 4 plus 4, which is 8. The numerator stays 2, and then you'd have 1/4. So this means that f prime of 8 is 1/4. For part B, we want to use the derivative of f prime of 8 to find an equation of the tangent line to the graph at that point. So we know that f prime of 8 is the slope, and we also know that f of 8 is 4. So using that point slope formula, we have y equals f of 8, which is 4, plus f prime of 8, which is the slope, 1/4, times x minus the x value we use, which is 8. So here we have the equation of the tangent line. Now we could solve this for y and you get 1/4 x plus 2. Now we're going to graph everything in Desmos. Here I have the function root 2x. You can easily graph the point by typing it in. Now I wrote it as 8, 4, but you could also have Desmos plot the point by evaluating it at the function. Instead of 8, 4, type in 8, f of 8, and it's going to get the point there. We can label that point. And then in the third line, we're going to type in our equation of the tangent line. And you can see you have the equation of the tangent line graphed right there. Another neat thing you can do is you can do this all in function notation, right? Y equals f of 8 plus f prime of 8 times x minus 8. And you get the same thing. It just graphed it in red. You could see by turning them off and on, it's the same exact graph. Another situation that comes up is dealing with numerical data for which no function is given. So we'll take a look at an example here. This table lists several values of a function y equals f of x that is continuous on the closed interval -1 to 7 and has a derivative at each number in the interval -1 to 7. That information is important, that the function is continuous and that it has a derivative at each number in the interval. We'll talk more about that later, but just know that these pieces of information are important. We want to approximate the derivative of f at 2 and use proper notation. Now, there's several ways to approximate the derivative of a function defined by a table, and each of them uses the average rate of change to approximate the rate of change, which is the derivative of f at 2. With this situation, each of these 3 methods is going to be appropriate. You don't have to do all 3. Any one of them will work. So the first one is to use the point that you're trying to find the derivative at and the point after it, so 2 and 4. So f prime of 2 is approximately 32 minus 12 over 4 minus 2. In other words, it's the average rate of change from 2 to the next point closest to it. And this is going to come out to 10. The second way to approximate f prime of 2 is to use the point at which you're trying to approximate and the point that came before it. This would give us 12 minus 3 over 2 minus 1. And in this case, the average rate of change would be approximately 9. We got different answers because we're using a different method to approximate it. The third way to approximate it is by averaging these two results. So 10 plus 9 over 2, which is going to be 19 over 2. Now, if we're talking about the AP exam, to earn points on the AP exam, when you're approximating the derivative of a function using a table, you have to use the interval that most tightly bounds C. This example, the value at which you're trying to approximate the derivative is not on the table. So in this one, we have another function that is continuous on a closed interval and has a derivative at each number in between. We don't know what those values are, but those are important characteristics of this function. If we want to approximate the derivative of f at 3.4, what this is saying is getting f prime of 3.4. This is going to be approximately, we can't get the exact because we don't have the function to do the limit definition. What we need are the 2 points closest to 3.4. 3.4 is not on the table, but we can use when x is 3 and when x is 4. So the change in y would be 1 minus 2. And the change in x is 4 minus 3. So you'd have negative 1 over 1. F prime of 3.4 is approximately negative 1. All right, guys, that's it for this section. Hope that was helpful to you. Reach out if you have any questions and take care.